morning, my dear students. Today we're going to continue the discussion on the inverters we started yesterday. So let me share my slides with you. All right. So if you remember, we were discussing, my dear students, the functionality of a full bridge inverter, in which we have 4 switches, which here in this circuit, the switches, the ideal switches are shown as bipolar junction transistors, NPN type bipolar junction transistors. Excuse me, and you remember the functionality of the 4 diodes, D1, D2, D3, and D4, which are shown here with green color, are there to protect our devices, our switches from over voltages, and also they are there in order, connected as it is shown on this circuit, in order to decrease power losses by allowing the energy which has been stored in an inductive load, in the case in which your load is highly inductive, the energy stored to return back to the source, to the DC voltage power source with a voltage Vs, which is connected at the input of this full bridge inverter. And you remember I gave you as a quiz, and also I explained to you in detail a switch which was switching on and off an inductor, and you remember we used this number circuit in order to protect the device, whereas all the power all the energy which was stored in the coil was finally transformed to heat in a resistive, the resistance which consisted of this number circuit. Here, we are in a better position to use these diodes, apart from protecting, I repeat, the over voltages across the switches, the real electronic switches, which may be bipolar junction transistors or may be MOSFETs. Apart from protecting them from over voltages, we also increase the efficiency of the system, I repeat, because the energy which may be stored in a highly inductive load is returning back to the DC power source. Now let's see how we can proceed with the analysis of such an inverter. In other words, our goal now is to find an expression for the current flowing through your load as a function of time. As in the case of DC to DC converters, we assume that the current consists of 2 terms. So it is the sum of 2 terms. One term is due to the forced response of the circuit, whereas the second term is due to the natural response of the circuit. And we can write the equation you can see on your transparency, on this transparency, that IO of T is equal to the sum of IF of T, where IF of T is the component which corresponds to the forced response, and IN of T is the component of the current which corresponds to the natural response. If we assume that during a period of time, during a time slot, if you remember, we discussed yesterday the waveforms, the voltage waveform across the load when the load was resistive, of course, just to use a simple resistive load. We had a square waveform across the load, if you remember. And assuming that the load is resistive, then in this case, we can assume that the current flowing through the load, through this resistive component of the load, can be expressed by using Ohm's law, by dividing the voltage across the load for this time slot. And this time slot, if you remember, it was half of the period, from 0 up to the half of the period. You divide it by the resistance of the resistive element of the load, so you find this is how you can find this this part of the current which is due to the forced response. And now let's come to the natural response. The natural response is what happens when the inductive part of your load is considered. So as you remember in other cases, the inductive part of the load which contributes to the natural response part of the load current can be expressed as a function of time, but the time is varying exponentially, as we can see. And also it's proportional to a constant capital A shown on this formula. The value of this constant capital A can be calculated from the initial condition. And also the fact that tau is the time constant of the load, which consists of two elements, one resistive, one pure inductive. And of course, as you know, tau is a ratio of L over R, where L is the inductance of the inductive part, and R is the resistance of the resistive part of the load. And at t equals 0, you would expect that the current must be minimum, must have a minimum value. From these conditions, initial conditions, and knowing how to calculate the time constant tau, we can find, and assuming that we have a minimum current at t equals 0, at 0 time, at the beginning of the switching, we can calculate the constant very easily, the constant, the value of the constant capital A as it is shown at the bottom of the slide. At time instance t now, in the half of the period, in other words, when the time t is equal to a half value of the period, if you remember, transistors T1 and T2 must be open. At that time, transistors T1 and T2, which were closed in the previous time slot between 0 and half the period, were closed and now they are opening. Whereas at this time instance, transistors or switches T3 and T4 close, as I explained to you in very detail yesterday. So the voltage now across your RL load becomes negative. It becomes minus V naught. And the current now will have a similar form as it is shown on this transparency, but the values of the voltages will be reversed. So a minus sign will appear on both the forced response and natural response parts of the current. And this is valid for the time slot between half the period and up to the end of the period, capital T. Again, a new constant, capital B, appears, as you can see in the formula, and again, the value of this constant can be calculated again from the initial condition. The fact that tau is still the ratio can be calculated as the ratio of L over R at time T equals half the period, where we would expect to have a maximum current flowing through the load, I max. So by knowing the value of tau, knowing the value of VDC, value of the resistive component of the RL load, and the value of I max, we can express the value of capital B as it is shown as the sum of I max plus VDC over R. And finally, in steady state, the current waveforms for the RL load can be expressed by this complex equation, finally, as a function, of course, how the current varies as a function of time at the first half of the period when switches T1 and T2 are closed, whereas switches T3 and T4 are open. And for the next half of the period, up to the end, from the half of the period up to the end of the period, when T1 and T2 are open and T3 and T4 switches are closed. So we have, as you can see, this complex equation. However, an expression can be obtained for I max by evaluating the first part of IOT at a time instance T equals half of the period. It is supposed that we know the switching frequency, and consequently we know the period of the periodic switching of the switches, of the couple of switches. So we can calculate I max, as you can see, and by symmetry you can calculate minus I max by substituting minus I max for I minimum at the same time instance. In other words, T equals capital T divided by 2. Finally, we obtain a formula from which we can calculate I max and I minimum in this case of a full bridge inverter, where again, I repeat, just to remind you, I max and I minimum are the values of the current flowing through your load at the output of the inverter. So we get again a rather complex formula from which we can calculate the values of I max and I minimum when we know DC voltage of the DC power input voltage source. We know the resistance of the resistive component of your load, and also we know the switching frequency. In other words, we know the period of the periodic switching of the couples of the switches, and also if we know the value of tau, which can be easily calculated, as you remember, as the ratio of L over R. Having calculated a maximum and minimum values of the currents flowing through the RL load in output of an inverter, of a full bridge inverter. The next case is to calculate the power which is absorbed by the load. And as you remember, if you have an RL load, when L is assumed to be ideal, all of the power will be absorbed by the resistive part of the load. In other words, you have to calculate the power absorbed by the resistive part of the load in this case. And as I told you, when you come to the calculation of power, you have to use RMS values of currents and RMS values of voltages. So it is necessary here to calculate the RMS value of the current flowing through the resistive part of the load, and of course through the inductive part of the load, which is connected in series, and multiply the square of the RMS value of the current by resistance R of the resistive load. And when you come to the calculation of RMS values, you must remember what and how we can do that by applying the definition. In other words, we take the square roots of, we have first to calculate the integral over the period of the time varying quantity, in this case I of t, of the square of this time varying quantity as it is shown at the bottom. Here, this is the definition we have used so many times in so many examples up to now in various cases. So you have to take the integral over the period of the square of the time varying current and then divide the result by the period. And finally, you take the square roots of the result, and this is the RMS value of the current in this case, as it is shown as it is shown in the formula, which is shown here at the bottom of the slide. Accordingly, if you wanted to calculate the RMS value of the voltage across the load, again, you have to apply a similar formula in order to find the RMS value of the voltage across the load. However, now we have an expression of how the time or how the current varies with time in this RL load, and consequently we proceed with the calculation of the RMS value of the current flowing through the load. And so finally, we substitute I square of t in this equation, we obtain finally, as you can see, a formula from which we can calculate the RMS value of the current flowing through the resistive part of the load, and then we multiply the square of this value by the resistance of the resistive load, then we find the power, which is the AC power, which is absorbed by the RL load, in other words, only from the resistive element of the RL load, given, again, I repeat that the inductor is assumed to be ideal. And on the other hand, this power which has been absorbed by the load, of course, it has been provided by the DC input power source with a voltage VDC appearing across its two leads. So we can calculate very simply the power which is supplied by the source, which, given that we have assumed that all elements in the circuit are ideal, in other words, we don't have any losses, we would expect that it's the power supplied by the source must be the same as the power which has been absorbed by the load, and we just calculated. The power from the DC source can be easily calculated by multiplying the voltage across the DC power voltage source, VDC, by the current which is provided by the source, which here is shown as IS. Any question up to now, my dear students? No question. Now, let's proceed with an example to see how easy it is. But in order to perform all these calculations, you need a scientific calculator, more advanced calculator, not just your mobile phone, the calculator which exists in your mobile phone. You have to use a proper scientific calculator. Now, let's see what happens with this example to see how we proceed with the calculations, which we saw just for the RL load. Now, let's assume that we have a full bridge inverter which has a switching frequency sequence that produces a square wave voltage across an RL load. And let's assume that the switching frequency is 60 Hertz. The DC voltage across the DC power source at the input of the inverter is 100 volts DC. The resistive part of the RL load is 10 ohms, whereas the inductive part of the RL load is 25 millihenries. And the question is how we proceed to find an expression for the load current. We just did it theoretically a few minutes ago. The power absorbed by the load, I have shown to you how to calculate the power absorbed by the load. You have to find out the RMS value of the current through the load. And finally, the average current in the DC source, which we assume to be capital IS. Now, knowing how we solve this problem, knowing the switching frequency value, which is of 60 Hertz, we can calculate the periods as 1 over F, so we can get a period of 0.0167 seconds, or 16.7 milliseconds. Knowing the resistive and the inductive part of the RL load, we can calculate the time constant tau. The value of the time constant tau comes out to be, by taking the ratio of L over R, comes out to be 0.0025 seconds, or 2.5 milliseconds. And finally, if we divide value of the period by 2 times the value of tau, we obtain a value of 3.33. And we are doing that because in all equations we derive for the maximum value of the current, the minimum value of the current. If you remember, we have an exponential term where the exponent is minus capital T divided by 2 times the value of the tau, the time constant tau. So by replacing in the formula we derive for the value of I max, which must be equal to the value of minus I minimum, if you remember, replacing the value of ADC, the value of the resistive load, and the value of the ratio capital T over 2 times tau, we obtain a value of 9.31 amps, 9.3 amps. for the values of I max and I minimum. And then we have to use the formula we derived for the current as a function of time through the load. Again, we replace the values of the variables and we obtain that when for the time slot corresponding to half of the period from 0 to, in other words, to half of the period, we obtain a value for the current as a function of time, which, as you can see, comes out to be a very simple equation with a fixed and exponential term. As you can see in this part, if we replace the values, we obtain this equation, which shows to us how the current varies as a function of time for half of the period, the first half of the period. And of course, we can do the same for the second half of the period. If you remember, when the voltages have been, the sign of the voltages was reversed, and we obtain again another formula, and finally, for the second half of the period, we obtain this formula, which shows to us how the current value varies with time. As we can, it consists again of a constant term, minus 10, plus an exponential term, as you can see at the bottom of the slide. And in order to calculate the RMS value of the current, and consequently to calculate the power absorbed by the load and the resistive element of the load, in actual fact, we take the square of this time varying equation for the current, and then we integrate this square variable, as you can see in this equation, divide by the period and take the square root, and we find out that the value of the RMS value of the current flowing through the load, capital I RMS, is equal to 6.6 amps. And consequently, if we multiply the square of this current, the RMS value of the current, by the resistance of resistive part of the load, we find, as it is shown here on this slide, that the power absorbed by the load is 441 watts. And what is missing now is the average source current. In other words, we can calculate the average source current by equating source and load power, and from this we already calculated that the power absorbed by the load is 441 watts, and we know that the power provided by the source is very easily, I told you, and very easily to understand, is the product of the average source current and the voltage across the source, which is 100 volts. And by dividing the power delivered to the load by the voltage across the source, we find the average source current, which is provided by the source, and comes out to be 4.4 amps. Any question up to now, my dear students? No question. Okay, let me go back. Now, I would like to discuss with you the waveforms across an RL load, or the waveforms generally in a full bridge inverter when the load is RL. It consists of an ideal inductor and a resistive part. So as you can see here, the voltage across the load is expected to be a square wave in the ideal case, without any dead time, as we explained yesterday, which of course is required in order to take into consideration the switch on and switch off times required for the real electronic switches to turn on and off. So in the ideal case, the voltage waveform which will appear across your RL load, it will look as it is shown on the top graph. In other words, as a function of time, having a periodic switching with a period capital T, you would expect that the voltage across the load to be positive for half of the period and then becomes negative minus VDC for the rest of the period, and the thing is repetitive because we have steady state. The current now, as you can see, it varies exponentially from a value I minimum to a value I maximum. And the variation is symmetrical again around 0 amps, as it is shown on the second graph, where the variation of the current flowing through the load, the RL load, is shown as a function of time. So when the switches, the couple of switches T1 and T2 are turned on, whereas the switches T3 and T4, going back to this diagram, when switches T1 and T2 are closed, whereas switches T3 and T4 are open, then you would expect to have a current flowing through transistor T1 through your load and go back to the source through transistor T2, whereas T4 and T3 transistors are off, open as switches. And then you would expect in a steady state situation, when in other words you have repetitive switching on and off of the pairs of the 4 switches, the current will increase from this minimum value to a maximum value exponentially. And then when we have changeover of the switches, in other words, switch T1 and T2 are off, open, and switches T3 and T4 are on, closed, in other words, the switches, then you expect the load current to decrease again exponentially, given that the voltage across in the RL load has been reversed. It became now minus VDC. So you would expect for the current to vary again exponentially as a function of time, and from I maximum goes down to I minimum, which is a negative value for the current. And the same thing happens given that we're in steady state. And this exponential variation is, of course, described, you see, by this equation here, that how the load current I of t varies with time for first half of the period and the second half of the period. So for the first half of the period, you see you have a constant term. So at t equal 0 time, you have a constant term VDC over R. And at the end of the period, of the half of the period, if you replace t with the half of the period, you get the maximum value of the current. But you see that in both cases, both in the first half of the period and in the second half of the period, the equations which show to us how the load current varies with time, both of them, they contain an exponential term, this one here. An exponential term which depends on the time and depends on the value of the time constant tau. And this is exactly what you would expect to see if I go back here. It's exactly these equations describe mathematically the behavior of the load current, which varies from a negative minimum value to a positive maximum value, which we call here I max and I min, minimum and maximum voltage currents, and the current swings around 0 amps. Accordingly, one can show how the current flows through the switches, as you would expect. The current flowing through the switches is shown here, switches S1 and S2 on the third graph as a function of time, and the waveform of the currents which flows through switches S3 and S4 in relation to time. In other words, when they are off for the half of the period, the first half of the period, and when they switch on for the second half of the period, when the switches S1 and S2 are off, open as switches, you can see that the current varies accordingly. And finally, you have a graphical representation at the bottom of this slide of how the current, which is provided by the DC power input source, varies, IS in other words, varies with time. And you can see, as you would expect, that this starts from a minimum value and goes up to, as you can see, to a maximum value for the first half of the period, and then it drops to 0 and continues again the same way. Any question, my dear students? As you can see, calculations are simple as far as you have a scientific calculator. And everything, you have all the background in order to derive the appropriate formula in the case of a rather complex RL load, in the case of a full bridge inverter. Any question? No questions. Now, something which is of practical importance is how we can turn on and off the switches. And in this case, I have again here the full bridge inverter with the 4 switches, and I'm showing to you only switch S1 and S4. So when switch S1 is closed, switch S4, if you remember, must be open. And the question is that we have 0 volts at the other end of the bridge, at the bottom of the circuit. So if this is a transistor, either a bipolar or a MOSFET, you can easily apply a voltage required to turn it on and off in respect to 0 volts. Because, for example, if you have a bipolar junction transistor, NPN type, and you want to switch it on and allow current to flow between the collector and the emitter, you have to apply at least 0.7 volts between the base and the emitter. The emitter of this bipolar junction transistor, which has the position of switch S4, the emitter is connected to the ground. So if you apply a voltage difference, a pulse, if you like, of at least 0.7 volts between the base and the emitter, this 0.7 volts will appear between the base and the emitter, so the switch will turn on upon the application of a pulse of a certain duration, a voltage pulse. However, if you try to do the same with the switch S1, where you have, let's assume, another NPN type bipolar junction transistor, in order to turn it on, again, you must apply a pulse between the base and the emitter. However, the emitter now of this bipolar junction transistor, it does not refer to the ground, to 0 volts, but it refers to this node. And this node may have a high voltage potential. In other words, this node may be 50 volts above 0 volts, above the ground. So you have to apply a voltage of 100 and a pulse in reference to the ground, which has to be applied now on the base of this bipolar junction transistor, must take into consideration that the emitter is at 50 volts. So the pulse must have a height in respect to the ground of 50 point, at least 50.7 volts or 51 volts, which practically is impossible because the voltage also at this node may become 100 depending on the voltages which we are using, or it may be 300. So in order to turn on transistor S1, which acts as a switch S1, we have to do something similar we did with the, if you remember, with the firing of the thyristors. In other words, we have to use a coupling transformer, an isolating transformer, and with the secondary coil of which is connected between the base and the emitter of this switch. And in this case, exactly the same way as the firing of thyristors on the upper half of a full bridge control rectifier are turned on and off. The same principle can be applied here for the switches which are on the upper half of the bridge inverter. And just to remind you, we use a so-called pulse transformer drive, which provides us with insulated switching. And you can find in the market of the shelf great variety of pulse transformers for every application in the case of power electronics. In other words, to drive thyristors, to drive bipolar junction transistors, and to drive MOSFETs. So the use of a pulse transformer eliminates the need for a separate drive power supply. However, there is a drawback in terms of the power consumption of a drive circuit. We have some losses there, but this is unavoidable. A pulse transformer is sometimes used to isolate a MOSFET switch from its driver in order to protect the drive circuit from the MOSFET's trouble. And this figure shows an example of a simple circuit which is used to turn on, if you like, a MOSFET switch, which is shown here as switch Q1. And we have some Zeners, as you can see, only one Zener and one diode at this primary coil of this pulse transformer. And the purpose of this Zener diode is to quickly reset the pulse transformer in order to be able to increase the switching frequency of the switch Q1, which is connected to the secondary coil of the pulse transformer. And of course, the pulse transformer that is switched on and off by, again, another semiconducting switch, either a bipolar junction transistor or a MOSFET. Any question, my dear students?
Thank you.
And again, going a bit further, as you can see here, we can use a transformer isolated power supply for these low voltages which are needed to switch on and off the 4 switches, 4 MOSFETs or 4 bipolar junction transistors existing in a bridge inverter. And here I'm showing to you again only half of the inverter. In other words, one string which contains, as you remember, 2 switches, switch Q1 and Q2 on the same string. So when switch Q1 is on, in other words, close the switch, and current flows between the drain and the source to the output, the other switch Q2 must be off, in other words, open as a switch, so no current flows between the drain and the source of switch Q. I repeat, when switch Q1 is on, closed like a switch. And this can also be achieved by using a transformer, as you can see here, with a double secondary coil. A secondary coil consists of two independent coils. We have two secondary coils of the appropriate turns ratio, of course, which are not shown here. And then we fully rectify the output of each one of these coils. We further use a voltage regulator, a three-terminal voltage regulator, in order to power the gate drive circuit of a MOSFET switch, as it is shown here. So in this case, again, because this middle point, the common point, is isolated, it's very easy to use it. This is an alternative, if you like, of how to use, how to drive the upper part of the switches in a case of a bridge inverter. So, any question, my dear students? I think I will stop here for today. I wish you a very good weekend. And also, if you listen to me, please, all of you, you must check the Moodle, because I have uploaded your homework number 2, my dear students, which will be available tomorrow evening. And also, next Wednesday, the 25th of August, the same time, you are going to take the online quiz, the second quiz, which must be done online according to the regulations. And this quiz will be available next Wednesday at 9 o'clock. So at 9 o'clock, be prepared, please. Be prepared for the online quiz. The questions of the online quiz are related to DC converters. How to design, for example, a buck converter or a buck boost converter or a boost converter. So please go back and see all the examples I have solved for
Which
you.
chapter, Doctor?
Sorry?
Chapter. Which chapter for quiz online?
DC to DC converters.
DC converter?
And in particular, buck converter, boost converter, and buck boost converter only. Okay. I have solved for you. This week I solved 7. I solved 7 examples for you with DC to DC converters, because before starting the inverters. You remember? And also I have solved for you a lot of examples during my teaching. While I was teaching to you DC to DC converters. So concentrate on DC to DC converters, but the 3 types of converters. And also you must remember the topology. And don't forget, you must remember the topology of each one of the 3 main DC to DC converters. In other words, you must remember the topology, the circuit topology, I mean, of a buck converter, of a boost converter, and a buck boost converter, please. You must remember how to draw the circuit, where to put the switch, where to put the diode, where to put the inductor. Okay, my dear students, so be prepared. And also all your cameras must be prepared so early in the morning next Wednesday, when we will meet again together to perform the online quiz, you must be prepared to switch on your cameras, okay? And I must see your hands. Your cameras must show at least your hands, according to the regulations. Furthermore, from what I know, you finished, or you are going to finish today with the lab. I think today you have a lab exam, is that correct?
Yes, Rector.
Okay, I wish you best of luck with your lab exam. And next week, you don't have any lab anymore, from what Samir told me a few days ago, because he's leaving on the 30th of August. He's leaving for good. He's going back to Kashmir, I think. So we stop here. Also, tomorrow at 7 o'clock, you will be able to download homework number 2, which contains several questions, several problems, which must be solved, and the solutions must be uploaded to the Moodle, my dear students, before the deadline. But I don't remember now to tell you exactly what is the deadline. Everything is written in detail on the Moodle. So please, as soon as you have free time today, visit the EE365 Moodle page to see what you have to do and for what you have to prepare yourself to download tomorrow evening the homework number 2 and to see exactly when the online quiz will take place, as I explained to you. Thank you very much for your attendance, my dear students. I wish you a very good weekend and see you again next Sunday. Thank you very much for your participation. Have a good night. A good day for you all, my dear. Do you listen to me? Thank you for your attendance.